Good morning. Welcome to Krishna's classroom. We shall continue with our exploration of compact spaces. Now, before we go any further, we'll just consolidate what we said earlier, namely on the relationship between continuous functions and the compact spaces. So, we'll just recall, this is a summary of the relation. Compact spaces and continuous functions defined on the means not only real valued functions but defined from the with this particular compact space as the domain. Okay. So we have proved the following results. The first result that we have proved is that if f from x to y is continuous, was x compact, then f is called. So what it says that if the domain of the continuous function is compact, we are talking about continuous functions from one metric space into another metric space. The domain of the continuous function is compact, then it is bounded. Okay. So, in particular, all continuous functions continuous real valued functions defined on closed bounded subsets of R bound. Now you know that in R, compact sets are classified as closed bounded sets. Okay. So, in fact, more generally, all continuous functions on compact, all real valued continuous functions defined on compact metric spaces are bounded. It's about the relation connecting compactness, continuity, and boundedness. So this is connecting compactness, continuity, and connected and boundedness. It's quite a general thing. The second result that we have proved is that any continuous function from a compact metric space to R attains its maximum and minimum at some points so we are taking x as compact metric space f is a map from or a function from x to R. It's a real value function which is assumed to be continuous. Then there exist points such that supremum of for x belonging to x and fx2 equal to infimum of. You want to understand these results. Now, first of all, you observe that if x is not compact but f is continuous, okay, and we have explored this. So, for instance, you take x equal to open interval 0, 1. This is not compact. There exists a continuous function on 0, 1, which is not bounded. You can be very specific. Take fx equal to 1 by x. So compactness plays a role there. Okay. Now the second statement goes still deeper, tells more about it. Now obviously if you take x compact and drop continuity, then you see the result may not. Okay. Now the second result, which goes still deeper, says that if f is bounded on the interval 0, 1, I am talking about the compact interval 0, then you see that it attains its maximum value, and you can actually show that there exists x1 and x2 where it attains its maximum and minimum. Okay, and clearly if it is continuous but the space is not compact, it cannot be accepted. Okay. Now the third one tries to connect the continuity, then convergence of a sequence of functions, the nature of the limit, and the nature of the convergence. Okay. So what it says is this. Third result that said. So x compact. These are the assumptions. Then you have a sequence of real valued functions fn from R n. So you have a sequence fn from x to R which is continuous. Now assume, further assumption is that for every x belonging to x, fn x is monotone. It could be both. So say it could be either it could be monotonically increasing or monotonically decreasing. So the assumptions are x is compact, fn is a sequence of functions which are continuous for each n, and for every x you have fn x is a sequence of real numbers, and we are assuming that they are monotonically increasing or monotonically decreasing, and further assume that are continuous and such that fn x converges to f of x for every x belonging to x. So there are a lot of assumptions. The first one, X is compact. Then you have a sequence of continuous functions, and we assume that they are monotone, X compact. Fn is a sequence of functions and Fnx is monotone. Assume that there exists f from x to r continuous and such that Fnx goes to 6. Then what we have is that Fn converges uniformly it will be very instructive to construct examples where these things are not satisfied. Okay. So convergence in this case implies uniform convergence. If it is compact, if you drop compactness, now you cannot make this or make this statement. Okay. Now the fourth theorem that we have looked at is this: any continuous function from a compact metric space X to a metric space Y is uniformly continuous. So continuity plus compactness assures the continuity is uniform. Okay. So these four results we have already proved, and we have also analyzed some examples where this could be, this has been incisively looked at. So compactness and continuity interact in a very positive way. We are asking what are the outcomes of that. Okay, now let us, before we go further, let me just look at one more example. Let f be a map from the open interval 0, 1. Now, this is not compact. Assume f is monotone. Monotone in the sense either it's an increasing function or a decreasing function, and bounded. Then f is uniformly now the strategy we use to prove this is, see, we try to extend f to a compact set containing 0. So Consider, take x equal to, this is compact. Now, we know that we are given f is a monotone and bounded function. Okay. And sorry, f is continuous. F is continuous, f is monotone and bounded. Then f is uniformly. So f is a continuous function on this. Now, since it is a monotonically, suppose you take a monotonically increasing function on the interval 0, 1. Then what happens? The infimum of the values, and it's bounded, and the infimum of the values of fx, so you see that limit C is the infimum fx x belonging to 0, 1, and supremum x's, because you see that we are assuming f is bounded, and this can be taken as okay, let us assume f is increasing monotonic. Then if it's a monotonically increasing function, it is something like this, increases, and it is defined on this interval. Therefore, you can extend the function continuously to the endpoint, and it is bounded. Bounded means that the infimum and supremum exist on this interval. Okay. Now let us write. So you have limit extending to 0 plus. One minus that means you can extend it to this. Now you consider what you do is, so you have continuously extended the function to the endpoints. Therefore, now define f is now extended to as and by the previous statement, then it implies f is uniformly continuous on 0, 1, which implies F is uniformly continuous on 0, which is contained in this is an example where even though X is not compact, but if it is monotone and bounded, then it can be extended to the compact interval continuously, and then that's a bounded function. Okay, that's a continuous function, and by the previous theorem that F is uniformly continuous. Okay, so these are the results that we have proved, and I suggest that you take examples incisively, look at these results or investigate these results in the case of some very simple examples to get insight into what these results mean. Okay, and now I have said earlier that how to analyze such things. What you do is you knock out some of the conditions from the statement and see whether the result is still valid. Okay, right? And how that will give you some information how the statement or the theorem depends on that particular property which you have. Okay, so construct good examples or analyze good examples, and that's the only way in which you can do this. Now we further continue with our exploration of compact spaces. So we continue with so our objective is to study the structure of metric spaces. So what is the basic property of the compact metric space? Say X is compact if every open cover for X has a finite subcover. That's important. For every open cover of X, it has a finite subcover. That is at the outset the definition of this. Now what this implies, what sort of things you can infer further on these spaces. So let us look at the following. Suppose XB is a compact metric space. Or is just a metric space. I mean, need not be compact. Compactness we can bring in. With an open cover UIC. Okay. Now you know that if it is compact, it has a finite subcover. So you have something like U1, U2, UK, a subcollection providing this with a cover. Okay. of ui for some k, finite k, which is a cover for x. Now, one of the questions that we ask is, suppose you take A is a subset of X such that diameter of A is equal to some delta. Okay. Now you see, the question that you ask is this. Suppose you take a delta. Okay. Right? Then does there exist a UI from the open cover UI such that A is now obviously the answer to this is that if you choose delta sufficiently large, then it doesn't work. Sometimes it is, right? For instance, if you take x to be equal to for instance, you take the interval 0, 1 and A to be the interval 0, 1 itself. Now, if your open covering contains 0, 1 or something that there is an open set which contains this interval 0, 1, then of course A is contained. There is a particular UI to which it belongs to. Otherwise, it doesn't happen. So it depends on two things. One, the choice of UI and the set A. This is not going to happen for all subsets of this. But the question that you ask is this. Suppose, does there exist some delta? Still we can ask this question. So the question is this. Delta positive such that diameter of A is less than delta such that for any subset some ui can be found such that ui. This is a question that you ask. And you know that if yes, then for any delta prime less than delta, this result. If it happens, now the question is, does it ever happen? What it has got to do with the compactness? Now you see that it is probably possible because for a given covering there is a finite subcover. Therefore, we are somehow in a position to squeeze a inside one of the ui's. So we will find it out. Okay, right. And we have to be more precise. We are not precise yet. Okay. So let us explore some examples. Suppose you take x equal to 0 and un you take as 1 by n 1 for n greater than or equal. Then what is the covering that you have? Then the covering that you have for 0, 1 is, it starts from here. This is 1 by 2 to 1, then 1 by 3 to 1, and so on, 1 by n to 1, etc. Okay. Then un is a zero one. Now let us ask this question. Okay. Suppose delta is a positive number. Okay. And you see that you take the a to be 0 delta. Okay. So this is the set that you have. Now the question that you ask is this: is A contained in any one of these? The answer is no. The answer is no. Why? Because you see that this is how the distribution of UNs work, and you see that for n sufficiently if you take delta, what you can do is you can certainly take a, or you take any one of these UNs, and A is not for any choice of N. A is not a subset of So you are talking about whether this is a subset or not in relation to a cover. Okay, right. Now let us take another example. Another example that we take is the same one. Example. Suppose x is the same as 0, 1. Now you take u0, you define, say, minus epsilon to plus epsilon. And un you define as the same thing. Greater than or equal. Then u0, or now we can take one. It's not the same notation, that's why I am taking this u0. u0 union, or u0 and this is an open cover for 0, 1. Suppose this is the open cover. That means we have adjoined with some this one where we have epsilon something positive, some positive. Okay. Now we look at this set. Take A equal to 0A, or I think we will enhance this class into this one. Yeah, just enrich this by taking UA equal to A to 1 for A belonging to 0. Then what you have is this. What you can say is this. No, for 0, 1. Let us choose a cover. Choose u0, find as -1/10, and then you define ua equal to a/2 to 1. a/2 for a belonging to now clearly a open cover for now you see, and it is also an open cover for one, where 0, 1 this is compact, whereas this is not compact. Okay. Otherwise it's now suppose you take a to be equal to 0, say okay, then what can you say about this? Now this is then diameter of a one by 10, and a is contained in u0. Now let us take any now what you can do is, suppose your a is equal to 0, 1 by 10, or sorry, 0 b, where b is greater than a does not belong to a does not belong to nor in any y or in any ua. because we are taking situations where A is positive and A is, see, you have A equal to 0. Okay. Okay. Let us take any a subset of 0, 1. Then infimum of A is equal to 0 or infimum of A equal to some A or A positive. These are the two possibilities that if equal to 0, then A is contained in and by. If infimum of A is positive, then A is contained in some A. Why it is so? All that you need is take infimum of A. Suppose infimum equal to A. Then you see that yes, A positive, then you are going to have A contained in. So you see that all zero one diameter less than 1 by 10 is contained in some UA or okay. So that is it. Now we look at a third example. Take the interval -1, that means 0 is left out. Okay. Now you see that minus 1 0 is an open cover X. Okay. Now there does not exist a that all A with diameter of equal to delta is in one of the covering you can easily produce one. Okay, suppose you take minus delta by 2 by 2. This is not contained in minus 1 0. This is also A is not contained in 0. Okay. No matter how small. So these are some of the incisive investigations into this. Now let us work out the details, or let us look at the consequences of all this, and then prove that if X is compact, then there is some delta for a given open cover. There is some delta positive such that all sets with diameter delta is inside one of the covering sets. Okay. So that's the theorem there. So before that, we will define what is called the or after statement of. We are going to associate with every compact set a number. What is called the effect number. Okay, so let us state the theorem first. Let and of course you know that compactness assures that there exists finitely many elements from this class which is a cover for X. what we state is this: then there exists a delta positive such that any A contained in X with diameter less than delta is in some ui so X is assumed to be a compact metric space, ui is a given open covering. Then what we assert is that there exists a delta positive such that for any A in a subset of X with diameter A is less than delta, is contained in some ui for I belonging to pi. We are not saying that it is in all the uis, it's in some ui on this. Right. And in fact, you see that if there is such a delta positive, then for any other delta prime which is less than delta, the same result occurs. So, Kumar, if in relation to the open cover ui, then for any delta prime which is less than delta, the same result. Therefore, see, we are now justified in defining a number which is the largest such delta possible. So the question is, so what we can is thus the largest delta with such a open cover, such an open cover for X is significant. In relation to open cover of X. Now we have already seen some examples where such a delta may not exist at all. Okay, right? Now what we are going to assert is that if X is compact, certainly there exists a delta. And this delta, when it exists, we say that the Lebesgue number A of the covering existing point. Whenever such a delta positive exists, and you get to the extreme of that, so such a delta is called a Lebesgue number in relation to the covering Ui, because you know that it's all related to the covering that you use a finer covering, and of course the delta is going to be small. Okay, so and what it says is that if X is compact, then there exists such a delta, or it has a positive Lebesgue number. Okay, so that's the statement that you are making. So let us now try to prove this theorem. For X belonging to X, Ix such that so the ui's are already given, and you choose an arbitrary x belonging to x which is in some uix. And you know that this ui's are, it's a covering for this. So you see that when you choose x, you see that there is an ix into which this belongs to. So this is the particular uix into which you happen to be. Okay. This is the open cover that you are working with. So there is a uix into which x belongs to, and there exists Rx positive such that the ball with center at x and twice Rx is contained in. That is because UIX is open. Entirely in that is the neighborhood that you have chosen. Now what we have is that since X is compact, where X is U1, U2, yeah, okay. Yeah, we will do. We'll look at this class now. Now you look at this collection. E, X, is an open cover for X. Because for each X, this is in one of these, and the union of all this is an open cover for X. That is since so there exists X compact. There exists finitely many XK such that X is contained in or X is equal to union of PXRK. Because you see that BX2RK is contained in this, therefore BXRK, see, this you observe. Rk is defined as Rx k. So we have got a finite subcover. Now let delta be less than they're all positive, so there's a minimum exists as a positive number. Let A be a subset of X with diameter let A be an element of then A belongs to B xk rk for some k. Now let x belonging to A. We compute this. Distance from x to xk is less than or equal to distance from x to A plus distance from A to xk, which is of course less than, this is delta, because diameter of A is less than delta, and this is of course clearly R2, and this is less than twice. So what do you have? Therefore, A is contained in B xk 2rk, which is contained in U I. So we have shown that given A with a diameter less than delta, and delta as chosen as specified in our analysis, there exists a subcollection Q into which A is contained. So that completes it. Okay. So that's the Lebesgue covering. Now it is just a remark, I am not going to read. You can look into the book. Is that we have proved that all continuous functions on R on a compact metric space are uniformly continuous. We have shown that all continuous functions all continuous functions on on a are uniformly. And in fact, need not be real valued also. It can be from more generally. If X is compact and F is X to Y, Y a metric space, and F is continuous, then F is uniform. Now a proof can be constructed. This theorem may be constructed using the Lebesgue covering level. I am not going to do the proof of this, but this is available in the book, and you can look at example 4.3.6. Okay, I think that's a place where we can stop today's lecture. So thank you very much.